Hello everybody, this is Dr. Ali Mugable. Today we'll touch on the following topics: correlative decoding, optimum receivers, and I pattern. Note that we have similar videos related before, and here we're just giving a general summary about the correlative decoding, optimum receiver, and I pattern. We'll start with correlative decoding, correlative level coding. We'll look at duobinary and modified duobinary. Then we'll look at M-ary, pulse amplitude modulation, followed by optimum linear receivers, and we'll touch on I pattern. So correlative level decoding. Correlative level coding, or what we call partial response signaling, is the addition of ISI. Here we introduce ISI rather than remove ISI to the transmitter in a controlled manner. Why are we doing that? To reduce the bandwidth, because once you expand the signal in time, the bandwidth requirement becomes less. That's contrary to the raised cosine scheme. Because in raised cosine, we solve the problem of ISI by increasing the bandwidth. The pulse is widened in time, resulting in ISI, but in a controlled manner. So the key word is here, the controlled manner. Introducing ISI at that transmitter, we have a known ISI, controlled. Hence, it can be removed at the receiver side in a deterministic way. The first type, one example, is to do the binary input sequence. Okay, we have, we'll start with the binary input sequence, 1 or 0, and we'll use polar representation where 1 is represented with +1 and 0 is represented with -1. Now we'll take A of K after, we'll take the sequence A, which is polar now, which has polarity, and then apply duobinary encoders, which means now every single coded duobinary pulse will be a result of the current bit and the bit that's before. So it's CK equal to AK plus AK minus 1. There is introduced ISI here, controlled way. So in the block diagram, it looks like this. The input sequence, which is already AK, not BK. It's not the bits. This is the polar sequence. It's going to be, we have a delay here to represent the coding, and then we add every one to its previous one. That's in an XOR fashion. That's, sorry, in addition fashion. So we have, it goes through the ideal channel, and then we have to receive the sequence. Remember that the sequence now is coded because we have introduced ISI. So duobinary coder has the following formula, and of course, if you want to see how to represent this model, we have the channel is going now to be modified. The overall transfer function is going to be h of n, which is the ideal, and the response of this system is nothing but 1, which is the direct path plus a delayed version of the path. So this gives you the transfer function, the overall transfer function of the correlative decoding. We can represent this if you take a common factor, the exponential. We can write in the following format, and this is equal to 2 cosine. Remember, here we are using the color code, so the purple here is equivalent to the purple here. This is divided by 2 equal to cosine, or this equals, sorry, this equals to 2 cosine. Now, if you want to look at the response of the system, if you plot this transfer function of the duobinary frequency response, of course, not including the channel, is going to be the filter. Now, it's not, notice that it has the minimum required bandwidth, 1 over 2 TB, or RB over 2. Of course, here you can see that we have the minimum required bandwidth. This is nothing but the phase. We have linear phase. And if you look that we have no edges here, we have a smooth spectrum, which makes things easier to represent compared with the sync. If you take the inverse Fourier transform of this, you'll find that this is equivalent to sending the following pulse. This is what we call the duobinary impulse response in time. So it looks like a sine signal. If we sketch it, if we plot it, then it looks like the following. This is the pulse that we transmit. As you notice here, it covers the pulse of interest and the next one. The response of the input pulse is spread over 2 signal intervals, and the decay now is not 1 over t, but rather 1 over t squared, right? So because you have 1 t here and 1 t there. As we increase the time, the decay is faster compared with sync. At the receiver side, we need to solve for AK. So we need to solve the equation where we get AK hat. We're having hat because we are estimating, because there is noise. It is equal to CK minus the other bit. The problem, of course, with decoding, the problem in decoding dual binary signals is the introduction of error propagation, because every single outcome depends on the previous one. And if you got the previous one wrong, so error will propagate. So the solution to the error propagation problem is the pre-coding, where we have the input sequence is pre-coded. Before doing the sequence, I will compare everyone with the previous one, XOR. And in fact, what we transmit is decay, which is the difference between the bit and the previous transmitted bit, which is basically sending the difference. And then, of course, we can get the polar representation followed by the dual binary coding. The beauty about this, that if we do the decision rule, the decision will be not dependent on the previous one. So CK, the coded bit, will be, if CK is greater than 1, you have P equal to 0. And if CK is less than 1, you get PK equal to 1. So there is no dependence on the previous and the one that comes after. Kind of we took the dependence of the difference at the transmitter side, where there are no noise. So let's look at the current example. We would like to do correlative level coding with pre-coding. So here is the original sequence of data. Now I will assume that this pre-coded sequence is 1. I changed the color here. This is an assumption. It could have been 0. So how do we get the first pre-coded sequence? We follow the following formula. The current D equals to the current B XORed with the previous D. So these two XORed give you 1. 1 XORed with 0, 1. 1 XORed with 1, 0. So this is how it works. 1 with 1, 0. 0 with 0, 0. Now if you want to go to the 2 level, that's relatively simple. We just have polarity. So 1 will give you plus, 0 will give you minus. For the dual binary coding, we follow the following formula. So the current and the previous A's will give you 2. 1 plus 1 is 2. Minus 1 and 1 is 0. So this is how it works. Minus 1 and minus 1 is minus 2, and so on. Now, how do we relate this to the original sequence? We follow the equation. If the absolute value is greater than 1, if it's 2 or minus 2, you get 0. And if it is less than, if the absolute value is less than 1, you get 1, like in this scenario. So I follow the following formula to decode. If you compare the transmitted with the encoded one, you find that we got back without the need to look at the difference. So there is no error propagation. The problem would be more interesting if we introduce some errors. The following slide shows you a modified dual binary, and in the modified dual binary case, the problem with dual binary is that we had a DC. We had a DC component. It's usually preferred to remove the DC, so we can send a modified dual binary where we have positive and negative pulses in sequence. So basically, what we transmit does not affect the next bit only, but with a minus sign. So if you look at the time domain response, it will have 0 DC. This is a frequency response. Also, we can generalize the form of correlative decoding. We can have introduced ISI not only on the next bit, but any bits before and after. We can expand the pulse in time more, so we have less bandwidth requirement, but the problem would be the cost of transmission, because the complexity of the decoding will be more. All right, now if you look at the baseband M-ary pulse amplitude duration, we are done with the correlative decoding. Let's look at the baseband M-ary transmission. In baseband M-ary transmission, the pulse amplitude modulator can produce M different levels. And the duration now is not called the bit duration, but rather the symbol duration. The signaling rate, of course, will be 1 over the symbol duration. So it will be 1 over t symbols per second. Please do not confuse sample in the sampling process and symbol. They are two different things. So the relation between the bit and the symbols, of course, the symbol duration is greater than the bit duration if we have more than binary. So remember that TB is bit duration, T sub S or just T is a symbol duration, M is the number of alphabets or in the M-ary communication. We can do one way or another. Of course, we can relate the time duration or the bit rate. Of course, the bit rate would be greater than the symbol rate or equal. In M-ary pulse amplitude modulation, the information is transmitted at a rate of log base 2 of m, faster than binary, of course. So you can see that this is the difference in the rate. In general, what we will sacrifice in M-ary communication, depending on what kind of modulation you have. If you use pulse amplitude modulation, then you get higher data rate, but if you want to keep the same amount of error, you need to pay the price in terms of power, as you already know. So the power factor, the increase of power factor will be m squared divided by log base 2 of m. That's a rough number. So there is advantage, there is disadvantage. And that's specifically for the case of PAM. Okay, now that we have looked at the two cases separately, noise and ISI, the question is, we'd like to have an optimum linear receiver. The receiver design of the baseband transmission system for additive white Gaussian noise alone is the match filter. This is the optimum receiver. And the optimum receiver for the case of ISI alone is the pulse shaping filter or the raised cosine. But if we have the two together, then we can solve the problem. We can combine the optimums. So we have, for combining AWGN and ISI, there are many receivers designed. We can use, if you have just one channel band limited, you can solve the problem with pulse shaping. But if in every call the channel changes, we can use an equalizer that changes at the beginning of the call. The simplest equalizer is the zero forcing equalizer. The problem with this equalizer that it's not optimal. It's not designed for noise. So it solves ISI but does not solve AWGN. So it's easy to design the zero forcing equalizer. It forces the ISI to zero, but it neglects additive noise. So it could result in amplifying the noise, solve one and worsen the other, which we call noise enhancement. The thing that solves the two together is what we call the minimum mean square error equalizer. Of course, at additional complexity, it reduces both effects of noise and ISI. Of course, it outperforms the zero forcing equalizer because it does not only zero force the ISI, it also takes care of the noise at the same time. So a summary of this slide, if we have combined ISI and AWGN, then we can use the matched filter for the noise. But then if we use just a zero forcing equalizer, we could worsen things, and we need the minimum mean square error equalizer to take care of both at the same time. So if you look at in terms of linear system representation, this is the convolution equation. What you get is the convolution of the impulse response of the receiver filter and the output of the channel. Okay, so for perfect operations, you want at the sampling instant, so at I capital T, you'll get one number out of this, and you want to compare this number with what you expect, AI. So the difference between the two is the error. Of course, we can have scale adjustment, but in general, you want to have defined this as the error. And what we want to optimize or minimize, not the average error, but rather the square of the error. Because if you look at the average error, then plus and minus could cancel out. You have errors, but some of them are positive, some are negative. So what you want to do is minimize the mean squared error. And this is what we call the minimum mean square error equalizer that takes care of reducing the error in any case, including noise and ISI. So the optimum linear receiver in minimizing the mean square errors is a cascade of two things: matched filter and tap delay line equalizer. Tap delay because it's like a delay line where we take all the pulses and compare them with the previous after to remove the ISI. If the channel characteristics are known or unknown or time varying, then we cannot use pulse shaping. We have to use equalizers, And if it keep changes, we need adaptive equalization. So if the channel is mobile or changing frequently with time during the call, then we need to do adaptive equalization. Let's recall some of the, I will put in there's one specialized video about eye pattern I have already posted, but quickly here we'll just give you an example and then you can refer to that video. You can search Muqabl, M-U-Q-A-I-B-L, eye diagram or eye pattern, and then watch the other video. But for now, just a quick review. The eye pattern or eye diagram is synchronized superposition of all possible realization of the signal of interest, including noise and ISI. So let's say that this is the sequence that you ideally transmit, and this is now the waveform. If we take these snapshots in time, vertical lines, and we put them on top of each other, ideally you get this, and over 2 duration you get that. Now, but because of the ISI, what you get is not pure open eye. It looks like an eye in pulse amplitude modulation. You'll get, because of ISI, because of what comes before and after, you get this kind of shape. That's called the eye diagram. It is a synchronized version. I'll take every snapshot and put it on the top of the other. From the eye diagram, we can extract many things, including we'd like to have the widest possible eyes opening because this allows you to sample at any time. Remember, this is positive, this is negative. This is just a result of ISI. So I can sample, and this is the best sampling time. But if the eye is wide open, I can sample still here, of course, with less error. This is the margin over noise. This is the amount of eye opening that we have. And also, it's called noise margin. This is the distribution of this is the distortion at sampling time, so the values could be different. This is the distortion at zero crossing, so it's not always cross at the same time. And the slope give you the sensitivity to timing error. If you have stronger slope, then with changing in time, the sensitivity would be higher. And of course, we have the timing interval over which the received signal can be sampled, and this is what we want to be wide. So you can pause the video and read all the descriptions and make sure that you get them straight. Here are some examples of eye diagram for noiseless quaternary system. Without noise, you can see that we have perfect eyes. And we have quaternary because we have 3 eyes, because we have 4 different possible levels. This is because of the ISI. Similarly, here we have 20 dB signal to noise ratio, high signal to noise ratio. It's very similar to the noiseless case. And of course, once we have noise at 10 dB, the signal level is less. You can see that we could have some problems here. The eyes start to close. Okay, in the previous slide, we have seen the effect of noise. Here you can see the effect of band limitation. Okay, so this is the original case where we have M-ary, PAM with M equal to 4. And if we take this through a low pass filter with the cutoff frequency, 3 dB cutoff frequency of F naught, if we transmit at 1 Hertz, for example, and then we have the band limitation at F equal to 0.5 Hertz, then you can see that the difference between the two cases here is that if for half of the bandwidth, we got the eye to close more. So we can think of the eye as a way of finding how healthy the system or the modulation is. That's it for the baseband communication. We'll again advise you to look at the specialized video for eye pattern if things went quick for you. Thank you for being good listeners, and we'll see you in coming videos.